Hi everyone, my name is Anupam Sopti. I'm a PhD student at the Indian Institute of Technology, Delhi. Today I'm going to be talking about VmAP, which is a fair metric for video object detection. Let's dive right in. So the problem of video object detection is that you have a video where the objects are present in multiple frames, and you need to find the bounding box of the object as well as the class of the object. That is, in this case, a boat. Yeah. And you have to do this for all the frames in the video. The current method of evaluation of such a task is that for each of the frames, you take the IOE of the predicted boxes to decide whether this is a true positive or the false positive. And then true positives and false positives are simply accumulated across frames. So the precision recall curve ultimately captures the performance across different thresholds. For one particular confidence threshold, you will be able to get one value of this PR curve. And for different values of the confidence threshold, you get this entire curve. The area under this curve is what is known as average precision. And this represents the overall performance of a detector across different thresholds. And the mean across different classes of objects is what we call VmAP. This is the standard metric being used in most of the object detection evaluation work. However, there are some drawbacks of VmAP when it comes to video object detection. First of all, it disregards all temporal correlation. The frames being treated as IID and therefore true positives and false positives being accumulated are in fact highly correlated frames. And there is limited visibility in whatever failures are happening during the video object detection. For example, did we miss a certain view for the entire object? Could a tracker remove the miss by actually extrapolating from the detections in the previous frames? So these questions have to be answered in some way for the evaluation metric. Let's consider this toy example. So in this toy example, I have three detectors, D1, D2, and D3. And on the x-axis, I have the frame number. So the person A and person B both are present in 10 frames. And the blank circle represents that the object has been detected. The crossed circle represents that the object has not been detected. So as you can see, D1 is able to detect these objects intermittently while it is skipping some frames. D2, on the other hand, is detecting all the objects for all the instances of person B, but it is missing all the instances for the person A. And for D3, it is detecting all the instances in the first 5 frames, but missing everything in the second half of the frame. This might be because, for example, the object appearance has changed. The object has come closer to the camera and therefore it's larger in size. Okay. But as you would see, for all the 3 detectors, the recall is exactly the same, right? Because you're missing the same number of frames in each of these detectors. So VmAP metric would actually rate all of these detectors to be equivalent, but it is not the case. For example, if we talk about, let's say, the first 5 frames and the next 5 frames. So consider these first 5 frames as a set. Why am I talking about a set? Because it is highly probable that the first 5 frames for this object are correlated. Therefore, if I'm able to detect something here, it is highly likely that I'll be able to take this and extrapolate it using a tracker or something else, right? So it makes sense to actually combine objects into a set while doing this. So if we look at the set level, D1 is actually detecting all these sets. And D2 is missing 2 sets and detecting 2 sets. And similarly, D3 is actually detecting 2 out of 4 sets. So the recall actually becomes 1 here and 0.5 in both these 2 cases, right? And this is obviously the better case because when put in the entire system, you just need to make sure that at least all the objects are being intermittently detected, so that whatever decision maker is going to follow this particular detector is actually going to be able to take that into account that there might be an object here. Okay, so let's move on to understanding how do you do this at scale in the entire video. So we introduce something called a timeline plot. Let's say this video contains 3 objects, object ID 0, 1, and 2. And on the x-axis, I have the frame number. So the green and the red dots, they represent the frames where this object has been detected or not detected. Now looking at this, you will get an idea of how many frames are detected, how many are not detected. And this is all that's actually seen when you're looking at the AP metric, right? But here we go an extra step. So using the ground truth, we will first see how many of the frames satisfy a particular unifying criteria. So the unifying criteria could be based on the application. Let's say in an autonomous vehicle, you want that any object at a particular location should be detected. So the object around its initial location will be clubbed into a set across frames. So for example, from the frame which is starting here to all the frames that are starting here, let's say the object has hardly moved from its initial position in the video. So we combine this entire set of frames in set of bounding boxes in the frames into a set. And then when the object has actually moved far from its initial location, we instantiate a new set. So we call this the violation of a unifying criteria with the first member of the previous set. So in this case, a total of 3 sets are formed. As you can imagine, for example, if the object were this, the object has moved from its initial location here to the final location in this place, right? And the centroids of the bounding boxes in the intermediate frames are shown in the red. So this entire location is actually considered the same location, and a detection within this entire range would be termed as a true positive for the set. Now, let us look at the object 1. So if the object is moving faster, you will actually have smaller number of sets. And finally, for the object 3, this appears later in the video. As you can see, there are no detections here. And it is a relatively slower object, so you'll see longer sets. But what is interesting about this is that when the sets have at least one detection, we call this a true positive, right? So most of these sets have been detected. But for the object 2, especially, the entire range of frames in this area was missed, which means this was actually a view which was difficult for the object detector. Similarly, this entire set has been missed. So our set-based formulation is actually able to point out which views or which kind of occurrences are being missed by the object detector. So there are a number of benefits for the set level analysis. It clubs together all the redundant information. Similar views do not get counted multiple times. It highlights the contribution of missed sets. So it has a higher weight in the average precision sum, hence increasing the sensitivity to the bias. And it allows a latency-aware analysis also, since counting at every frame is not necessary. Even if you're detecting once in the entire set, we're able to do this. When you're running in real time, you'll most likely be skipping a lot of frames in between, right? And when you're skipping frames, it is important to see whether you've missed the entire set when you were skipping frames. In that case, you'll have to run a faster algorithm, or whether you are missing a particular view in the same set. In that case, it is okay because a tracker will be able to take over for this. And finally, it also correlates better with the in-system performance, because you'll most likely be using a tracker in the final system. So the set level analysis actually gives you a purview into what it is going to look at when these detections are being passed on to a control system or a planner, things like these. So we conducted several experiments to test our metric. The first question that we ask is VmAP sensitive to bias? So to do this, we created synthetic detectors. We introduced bias systematically against certain attributes. For example, when we introduce bias against size, we make sure that the object detector is having difficulty detecting smaller objects, but is actually able to detect larger objects with ease. So we increase the probability of detection for a larger box. Similarly, we introduce this bias with respect to illumination. For example, whiter objects are more likely to get detected. Contrast higher contrast is more likely to get detected, speed as well as color. Okay, and what we notice is that as bias increases, even though MAP is almost flat, maybe even increasing a little bit, VmAP actually shows a huge drop in the numbers. So this indicates that VmAP is actually sensitive to bias, and it is going to penalize missing certain types of objects together more harshly. Now let's talk about the operating point. So even though we are looking at the entire AP as the metric for the object detection evaluation, ultimately your object detector is going to run at one particular confidence threshold. So from this entire PR curve, you're going to be able to choose one point, and you're going to get that value of recall along with some value of precision, right? But when you use the frame precision and frame recall to do these things, you're going to end up with an operating point that is going to produce a lot of false positives, because it is trying to maximize all the frames being detected. And therefore, it is going to set a lower threshold for the object detector. We noticed this in 4 of the detectors that we tried. So this is the precision recall, frame precision and frame recall operating point. And this is the set recall or the video recall and video precision operating point. What we noticed that is that at the similar level of video recall, for example, 86 and 84 in this case, we get a huge improvement in the number of false positives. The number of false positives, which was initially 108, has now dropped to actually just 1. And we see a similar improvement for all of the object detectors that we tested. And the surprising thing here is that the video recall is actually consistent. Finally, we test the integration of the tracker, where the intermittent detections of an object could, whether the intermittent detections of an object could be recovered with the tracker. And if an object is completely missed, the tracker will also fail. So this needs to be reflected in the experiment. And what we found was that there is a higher correlation of the set recall or the video recall metric as compared to the ground truth, which is the frame recall with the tracker. So look at the yellow line here. So the yellow line is the decreasing order of values for frame recall with the tracker. And frame recall is actually represented in blue, and the video recall is actually represented in red. As you can see, that the ranking of methods with respect to the frame recall with the tracker is very similar to the ranking that has been produced by the video recall, in this case, the red line. And to quantify this, we saw that there is a 9% increase in the Spearman coefficient when it comes to video recall as compared to the frame recall. Therefore, we can conclude that video recall is a better measure of the in-system performance rather than the frame recall. That's all I had to share. I hope you like this work. Please do check out our code. It is all open source. And if you have any questions, please feel free to reach out to Anupam Sopti at csc.iitd.ac.in. Thank you for your time.